Right, folks. I hope this is going to be helpful. It's a quick run through the assessment practicals. We did a lot of practical work, and these are the ones that could be on your exam. Okay, so clicking through this PowerPoint, here's the list. It's on that website that's referenced there. It's on the AQA website. You'll find it easy enough with a quick search. These are the official 12. Some of them are actually kind of two practicals in one, like organic liquids. The purpose of this video isn't to give you an absolutely detailed run through of everything. It's just to give you a reminder. Then you can go and focus your revision based around what you hear here. So, with no further ado, if we can just work out how to click the PowerPoint. First one was easy. We shouldn't spend too long on this one. I trust you'd agree. Making a standard solution. So really, this is an opportunity to be reminded about uncertainties and things that we haven't talked about for quite a while. Ultimately, it comes down to making a solution a very accurately estimated concentration. So it requires us to know what the mass of the solute is to a high degree of precision. So we weigh it carefully, and we're careful about getting all the solid in, aren't we? And then also using a volumetric flask, which is a high precision volumetric device, better than a beaker, which isn't really a volumetric device at all. The stirring bar in step 2 there is not something we had to worry about. We just stirred it for a while with a glass rod. But the point is we know the exact mass and the exact volume, and therefore we have a very accurate grasp of the concentration. Now, without waffling on about moles, because that's too easy at this stage in year 13, just to remind you about uncertainties. So for any pieces of equipment which have a continuous scale, such as a balance or a measuring cylinder or a burette or a stopwatch, the uncertainty per reading is simply half of the smallest increment. Whereas if you've got a single increment device, i.e. a volumetric pipette or a volumetric flask, those are the only two you've met, then you're given it. You basically have to be told what the uncertainty is. So on that picture there, hopefully you can see the balance in step 1. The mass of the solute is apparently 54.68 grams. To be honest, that might be the empty beaker, but let's just pretend that's the mass of the solute which has been weighed into a weighing boat or a beaker. So that balance is giving a mass to 2 decimal places, and therefore the smallest increment is 0.01. Yeah, like the smallest value you could measure would be 0.01. So the uncertainty per reading is half of that, because we don't know whether it's been rounded up or rounded down to 0.01. It could be 0.051 rounded up, or it could be 0.09. Oh, I better be careful now. Or it could be something like basically rounded down. Sorry, my brain's left me. Either way, though, because of the way we use a balance, even if we zero the balance, we're taking 2 measurements, even if the first reading is just a 0. So either way, all uses of a balance ever for us in chemistry involve an initial and a final measurement. And that's because we're always putting something on the balance, usually a weigh boat. Whether we care about the mass of the weigh boat or not, we're recording its mass. We might just be calling it 0. And then we're putting a chemical into that, because we never put chemicals directly onto the metal plate of the balance, do we? So we're always taking 2 measurements, because there's always the container and then the container plus the contents. And so like you have to double half the uncertainty. So the uncertainty in that mass balance there will be 0.01, which is to say double because of 2 readings, half because that's how we do it, the smallest increment. So it just becomes the smallest increment. So the uncertainty there would be 0.01 out of 54.68 if that was the mass of the solute used. And so you can work out this as percent if you want. Now, as for the volumetric flask, basically you'll be told what it is. I've said there on the slide, the uncertainty will be stated. You're not expected to have memorized any of this. Like a volumetric flask usually has an uncertainty of about 0.6 mil per 250, and a pipette is normally 0.06, but you'll just be told what to use if you have to use one at all. So when we calculate the percentage uncertainty of our final concentration, that is subject to the error in the mass and subject to the error in the volume, and therefore the error in the mass per volume or the moles per volume is the sum of the two. So you just add the uncertainties. Now, again, we definitely don't need to waffle on about titrations right now, so I'm just going to really get to the most obscure points on this, uncertainties. So the burette, just learn this one, please. Remember it if you haven't already. The burette the uncertainty in an average titer is 0.15 cms cubed. It's a bit of a funny one. That's 0.05 per reading, so there's an initial and a final. Again, even if the initial is 0, that's a reading. So there's 0.05 on the start, 0.05 on the end, and then there's this additional 0.05 that we throw in, which in vague terms is to do with the judgment of the endpoint. We never quite know what fraction of that last drop that we added to turn the endpoint over, to turn the colour, how much of that drop was needed. and we pretend that a drop is 0.05 cms cubed. On top of that, there's also the effect of the indicator, which is itself either a weak acid or a weak base. So it just is 0.15. So the uncertainty in the average titer is 0.15 of the average titer. And again, you'll be told what the pipette's uncertainty is. It's probably going to be 0.06. It might be 0.05. But you just express that as a percentage of the measured value, which is always 25. So your average titer accounts for all the titrations that were worth doing, i.e. all the concordant results. Your average pipetting is just always 25 because that's the only value you ever measure with a pipette. Now, just wanted to also take the opportunity to remind you about the existence of redox titrations. So they're titrations, and so everything we've just said is relevant there, except they're self-indicating. The classic is to use permanganate in the burette, which is purple in solution, and permanganate loses its purple color when it oxidizes something else, for example, ethane dioate or iron 2 or whatever it might be. And so the end point is when that last drop of manganate doesn't get reduced because we've run out of substance to be oxidized by the manganate, and so that purple color actually persists in solution, and so it's a self-indicating titration. I just wanted to mention that. Calorimetry. In 2025, paper 1, we saw a little bit of calorimetry extrapolation, so I don't expect there to be much in 2025 paper 3, but you never know. So just a quick reminder here, Q equals MC delta T is the sort of the bare bones of what we do with calorimetry. We measure the temperature change and then we convert that to an energy change. Q equals MC delta T. All 4 of those terms are with reference to the water, which is changing temperature. It's either some water having a heat from a flame directed into it because we're doing flame calorimetry, in which case that'll be sat hopefully in a metal calorimeter cup. It could be in a glass beaker, but that would be subject to a lot of heat loss. Or it's solution calorimetry, where it's an aqueous solution having either another aqueous solution added to it or a solid added into it. Either way, M and C and delta C, and therefore Q, are all with reference to the water. So if it's 100 grams of water changing temperature because 5 grams of zinc have been added to it and there was some acid in there, the mass to use is that of the water because that is what's changing temperature. Anyway, you need to check your notes for this. This serves as a revision reminder exercise rather than a thorough revision of every single piece of content that's relevant here. That might flag up a few things you think you should look at. Q's in joules. So if we want to convert Q to delta H, we need to divide by 1,000 to put it into kilojoules. And we also need to divide by the number of moles of limiting reagent, that which has been used up. Check your notes, go back to year 12 for that. Right, rates. There's plenty to say about rates, and I'm going to try and boil it down to a few real just like flags that you can go and be like, oh, okay, better check that then. So there are several different classic reactions that we do rates practicals on. Now, the official line for assessment practical 3 was it's all about temperature's effect on rate, and therefore a bit of theory that's not getting a mention in this video is that, temperature's effect on rate, we could do a series of reactions at different temperatures, and we could get the activation energy by some graph work via the Arrhenius equation. Now, that's not covered in this video. That's just a reminder that temperature's effect on rate, we can use data from such practicals to get to get the activation energy. What might the reactions be? Well, it could be something completely unfamiliar where they just tell us that there's a time taken or a rate until a certain endpoint. 2 of the famous ones, the thiosulfate clock reaction, you've been doing that since about year 10 or earlier. That's where, as you know, there's a certain amount of time passed before X amount of sulfur is formed, that which is enough to cover the X, and so you stop the timer at that point. And if you systemize that by doing it the same every time with all the control variables like total volume and so on, then you vary the variable that you care about, if it's concentration of one of the reactants, or if it's to get order, or if it's temperature, maybe to repeat that lots of times at different temperatures to get EA. Either way, you get something that you can use. The iodine clock reaction is a reaction that makes iodine as a product. The iodine causes starch indicator to go black. But the thing is, we put another chemical in. We put some sodium thiosulfate in, which reacts with the iodine and so slows the process down. So the thiosulfate is like a second reaction that deals with the iodine that gets made. Basically just buys us a bit of time until the iodine actually can persist in solution once all the thio has actually been used up, at which point you get an endpoint. Again, these are things to go and look at, but this is just a reminder that these are 2 of the famous reactions. Then there's kind of a bit of a curveball. I think this had a mention in organic in paper 2 of 2025, something to do with forming insoluble solids such as the silver halides. So that could be like a haloalkane reacting with NaOH. A halide ion's kicked out in that process. It's nucleophilic substitution. And if silver nitrate were present at the same time, then that silver ion could combine with the halide ion and make a cream or a yellow or a white precipitate. And we could actually monitor the rate of such reactions, again, using the sort of thiosulfate clock type disappearing X method. Anyway, so those are some of the ways that we could monitor rate. What else is there? Well, there's also so-called continuous monitoring, which is where we literally just keep an eye on how much product has been formed so far. Or it could be using colorimetry, how much reactant has been used up or colourful product has been formed so far over time. And again, then there's an excuse to start getting a graph on there and maybe a tangent line. If we were to take the tangent for a product formed over time graph, as you can see on the bottom right of this slide, if we were to take the tangent for that at time equals 0, that would be the so-called initial rate. And when you do all those rate equation type problems where you've got experiment 1 and experiment 2, and this is doubled, that's halved, and the rate has whatever, then when it says the rate has doubled, tripled, whatever, that's an initial rate. And the way you'd actually get that in practice is by taking the gradient of such a graph at time equals 0, then doing the whole thing again, plotting another graph, getting the gradient at that time equals 0 and comparing them. And if you double the concentration of this and the tangent has doubled, then the rate has doubled, then it's first order, and so on. So just be reminded is all I'm suggesting here. This is a slightly awkward one. There's not actually much to it. It's just making sure you haven't forgotten about this stuff. So we've got a load of inorganic test tube reactions. There's also a whole host of organic test tube reactions, things like the bromine water test and so on. Don't forget about the inorganic ones, though. I mean, the test for halides, we're talking about silver nitrate again, and then the ammonia solubility test. So one of those silver halides, AGBr, will dissolve in dilute. Won't dissolve in dilute, but will dissolve in concentrated ammonia. AgCl, the white solid, will dissolve in conc and dilute. Silver iodide just is insoluble, full stop, in any sort of ammonia solution. But what about the test for ammonium? That's one that I think we could quite easily forget about if we weren't careful. Well, ammonium is a weak acid. Ammonium is the conjugate acid of ammonia. And so if we put NaOH, or any alkali, with ammonium, a reaction happens where ammonium acts as an acid. It gives away its H plus to the alkali, forming ammonia, the gas. Now, ammonia smells, but we're not supposed to be sniffing it because we're responsible practical chemists. So I think characteristic smell probably isn't a good observation for ammonia. We're not supposed to be smelling it, but we could use red litmus paper. Red litmus turns blue in alkali. Blue litmus turns red in acid. So if we're testing for an alkaline gas, now ammonia is a base, so an alkaline gas such as ammonia, then red litmus would be a way to do it. We just want to moisten the red paper, and as the ammonia soaks into the water of the moist paper, it will react and turn back into ammonium ions and hydroxide ions and turn it red. Turn the red to blue. What else is there here? Carbonate, add acid and it fizzes. You could test the gas with lime water to confirm that it's CO2 and therefore that was a carbonate. Sulfate, that's going back to GCSE. Barium sulfate is a famously insoluble white solid. That also reminds us that the solubility of group 2 sulfates decreases down the group. Barium sulfate is really insoluble. So at the top of the group then, magnesium sulfate must be very soluble. And the trend for the hydroxides goes in the other direction. So magnesium hydroxide is insoluble, barium hydroxide is very soluble. Group 2, again, we could add sulfates or hydroxides to see whether we get insoluble solids. So if we were testing for magnesium ions, we'd probably want to add NaOH, white solid forms, because magnesium hydroxide is insoluble. Testing for barium ions, it's the same as a test for sulfate ions, except we'd add sulfate to see whether we get a white precipitate of barium sulfate. So we can add sulfate knowingly to test for barium, and kind of barium knowingly to test for sulfate. But then you've got the ones in the middle, which are a bit awkward. So that's where they're sparingly soluble. We're not expected to know any flame test colours for like strontium or whatever in A-level. That was left behind at the end of year 11. But see what we can do. On that note, just a quick run through this table then. Add sulfuric acid, effervescence, it's going to be a carbonate. It could be a metal, like a reactive metal, but I think these are ionic compounds. It doesn't actually say it in the question. It's not going to be a reactive metal, so it's not hydrogen, it's going to be a carbonate. White precipitate, when you add sulfuric acid, that's probably going to be barium ions, or the one above barium, which is strontium, because they are both insoluble or low solubility sulfates. Test 2, adding NaOH. A gas form that turned damp litmus red. That is an absolute screamer for ammonia has just been made. Red litmus blue, which tells me that test 2, substance B, contained ammonium ions, NH4+. Silver nitrate, the whole white cream and yellow precipitates, so I don't need to repeat that now. And then the ammonia tests to confirm which one it is. Also, a bit more just to really torture you with this. I think it's worth just being reminded. It's up to you how much more you do on this. So now we're told we've got these compounds of group 2 metals. So these are ionic compounds then. We're told which ionic compounds as well. We're told which group 2 elements. There's a lot of thinking that's required here. Some are insoluble, some are soluble. So again, we know that from the group 2 topic, we've got the idea of hydroxides being insoluble and sulfates being more soluble, depending on which end of the group 2 we're in. So for example, again, barium sulfate very insoluble, barium hydroxide very soluble, and flip it on its head for the other end of the spectrum. So the insoluble might be a clue there. We add acid and it fizzes. Well, it's a carbonate then, isn't it? The solution remains colourless, but heat is released. Heat released tells me that there is a reaction taking place. We're adding acid to it. So compound 4 is probably a hydroxide of some sort, something which is a base, but it can't be carbonate because it didn't fizz. I'm not going to do every single box here because I'll lose you. This is picking any of it. There's another CO2 forming with acid, so that's going to be a carbonate. Slight white precipitate, that's very vague. Compound 3, slight white precipitate with acid. This sounds like a hint at a quite soluble sulfate. So the solubility of sulfates in group 2 increases as you go up the group. There is a white precipitate, so it's not totally soluble. It's probably calcium. But there'll be other information in the question that helps you with that if you were required to do that. Okay, anyway, moving on. Here's how not to do it. Right, so now we're on to some organic prep. Distillation first. You'll probably recognize this picture. It's one that we've used in questions. It's one of those like circle or tell me what the problems are with this. So this is a really badly drawn distillation. First issue I see is that the water's flowing the wrong way. You remember that you always push water uphill in a condenser. Secondly, the neck is wide open. So number one, there's no thermometer there for us to check the temperature of the vapor that's being collected in the condenser as a liquid. But secondly, everything would just escape out the top there. So you'd have no product, you'd have no distillate. There's also an absence of anti-bumping granules, which I also thought should be mentioned. So what are anti-bumping granules exactly? They're basically small glassy particles. There's an image on the right there that might help you with it. They're just very small, totally insoluble, chemically inert. Think of it as sand or glass. This is good enough. What are they for? Well, they provide a surface, albeit a very small surface, where bubbles can form. So when we're boiling or refluxing or whatever it might be, when we're heating our liquid, here it's distillations, but we're boiling it. Ultimately, we don't want huge bubbles to form all at once because the sudden expansion of gas pressure inside the container might cause the glass equipment to knock around and bump a bit because there's literally like something pushing into the inside surface of it. And anti-bumping granules just alleviate that worry by only allowing the smallest possible bubbles to form. So the biggest bubble that can form when this liquid's boiling is one that can fit on the surface of these anti-bumping granules, and they're not very big. So you get lots of tiny bubbles instead of one big bubble, and it just prevents the problem of a sudden expansion of gas inside your equipment. So I think the absence of anti-bumping granules might possibly be a reason there. Since this is a mixture and containing organics, it's sensible to assume it might be flammable. It's going to be aqueous as well, but it could be flammable. So electric heater is a better option than, say, a Bunsen burner. Also a good spot, they're making a very small molecule. Propanone is one of the smallest organics that are out there. It's only got 3 carbons. So it will have a very low boiling point because of very weak intermolecular forces. And so keeping it under ice might just prevent the risk of evaporation. Here's a much better, still limited and also not labelled, but there's a better depiction of a distillation. The thermometer is where it should be so that we can get the temperature of the vapour as it enters the condenser. So we effectively get the boiling point of the liquid that's being collected. We'll assume this is organic chemistry, and so they really shouldn't be using a Bunsen burner. You can see the little flame there. You can correct that. At least the liquid's flowing the right way through the cooler, though, through the condenser, sorry. The coolant is flowing the correct way through the condenser. So it's a better diagram than the one above, for sure. Reflux, also nice and easy. This is another how not to do it diagram that I've copied from an AQA exam question. For a start, we never use a thermometer in reflux. So number one, also it shouldn't be sealed. We don't seal a reflux. Actually, we do want it open in case there's a risk of expansion of gas and gas escaping. No gas should escape, but just in case. The water's flowing the wrong way through the condenser again. They love that one. It's only worth a mark, but every mark counts. There's just no need for a thermometer in reflux. We don't care what temperature it is. We just want to boil it to speed up the reaction. But we don't want the gases to escape, and so we lose yield. because that would be, expensive. So the thermometer is just completely unnecessary. We don't use a thermometer in reflux. Here's a much better example. There's no thermometer. The coolant is flowing the right way through the condenser. That's to say it's been pushed uphill. We're not using a Bunsen burner because we assume these are flammable simply because they're organic, and it is open. The point is no liquid or gas, should escape because the condenser is cooling everything down, condensing it, and sending it back to the reaction mixture as a liquid where it just falls by gravity. It shouldn't be so hot that it actually escapes the condenser. That would only happen if your condenser wasn't on or if it was really, really hot. Either way, that'd be a fail. E-cell. Now, again, I'm not going to say too much on E-cell. I've picked another question where AQA have said, what's the problem with this? You can see from the diagram, they're using the standard hydrogen electrode, which has been forced into the left-hand position. You haven't been told here what the E values are. You know that the standard hydrogen electrode's E value is 0 by definition, and then everything is relative to that. But however, this one, the iron 2, iron 3 electrode would have a positive E value, so it actually should be on the right anyway. But remember, the SHE is just always on the right. I've put the standard cell representation down there. Again, because the SHE always goes on the left, I've put it in the blue box. That's what the cell rep for the standard hydrogen electrode just always looks like. It's always exactly that. Platinum solid, phase boundary hydrogen gas, phase boundary H+. The order, when we read a cell representation, you've got your metal electrodes, and if it has to be platinum, then so be it. But then when it comes to the 4 redox species, your BRA, your BOA, your worst and your worst as well, it always goes reduced, oxidized, oxidized, reduced. So we say ROOR, and you read them left to right. That's to say on the left-hand side, you've got the more reduced species. In this case, that's hydrogen in the 0 oxidation state, followed by the more oxidized version of it, hydrogen in +1. Then on the other side of the salt bridge, you've got the more oxidized, followed by the more reduced. That's 3 and then 2. So it goes up to the middle and back down in terms of oxidation state. What is wrong with this then? For a start, the standard hydrogen electrode needs 1 mole per dm cubed of of H+. And of course, sulfuric acid is diprosic, so that would actually be 2 moles per dm cubed of H+ there. Those are non-standard conditions, so that's no good. We're not told what the temperature is, so I think we just assume it's 298 K, which is therefore fine. The pressure is correct. It's not 1 atmosphere. It should be 100 kPa, which is slightly less than 1 atmosphere, so that's fine. If you look on the right-hand side electrode, for a start, the salt bridge as well, NaOH. Now, in theory, any ionic substance will do for your salt bridge. What you've got in your notes is that potassium nitrate, which is KNO3, is the best option. I'll come back to why in a second. NaOH here would not be suitable. Sometimes it might be suitable. Not here though, because number one, it will react with the acid on the left-hand electrode and affect the concentration of the acid, which means it's not standard conditions, even if it were 1 molar of H+. But also, we know a little bit about transition metal chemistry. These metal ions would form insoluble hydroxide precipitates. For example, iron with 4 waters and 2 hydroxides, which is a green precipitate, or the rusty coloured one that iron 3 forms with 3 OHs and 3 H2Os. So NaOH would interfere with both electrodes. It would neutralise on the acid side and it would form insoluble precipitates on the other side. So NaOH is not suitable. KNO3 is a good shout because all potassium salts and all nitrates are soluble. So there's never a risk of potassium nitrate causing unwanted insoluble precipitates. And also potassium nitrate is reasonably inert. Nitrate can be a little bit of an oxidizer under the right conditions, but in dilute aqueous conditions, nitrate doesn't do much redox-wise, so it's a safe bet. It's not going to interfere in any way. The other danger here, the other problem is that should be a platinum electrode. It's nice to see Fe in the Fe electrode, but the 2 redox species here are those in solution, iron 3 and iron 2. The Fe electrode there is just a conductor. It's just an interface where electrons can be transferred between iron 3 and iron 2 and be sent over or received from the other side. So it's just platinum there. Okay, moving on again. Oh, titration curves. So look at what it says at the top of the slide. All we're supposed to know about, well, in terms of practical, is a strong-weak combination. So, either a strong acid with a weak base or the other way around. The ones that we do all our calculations on are weak acid, strong base when it comes to things like the half equivalence question, which comes on the next page. Now, I trust that you're already quite comfortable with drawing the shapes of these titration curves. You can see the clip art that I've pinched off the internet here. You've got also strong acid, strong base. You've got the strong and weak combinations overlapped, so you can just compare the shape of it, the qualitative shape. There's not much more to say really than just be familiar with that. We've done a lot of good learning on that over the years, so I'm not going to waffle now. The only thing I would say is that when you've got a strong stroke weak combination, the equivalence point, the pH at equivalence, is pulled in the direction of the strong. So the graph on the left, we're adding strong base, for example, NaOH, to a weak acid, for example, ethanoic, and the pH at equivalence is greater than 7 because it's pulled up in the strong base direction. And in the strong acid weak base example on the right, it's the pH at equivalence is pulled down. Just to go back to the left-hand graph quickly, the reason why the equivalence point is greater than 7 at equivalence is because at that point it's neutralized. So all the moles of weak acid have been neutralized by an exact same number of moles of NaOH. So at that point it's just like salt solution, like salt water. Now if it was HCl and NaOH, that would just be sodium chloride solution. But if it was ethanoic acid and NaOH, that's sodium ethanoate solution. And ethanoate is a weak base. It's the conjugate base of a weak acid, so it's also a half decent weak base. And so the solution is basic because it's a solution of a weak base. Whereas if it was strong acid, strong base, like HCl and NaOH, chloride is a really rubbish base, so NaCl is neutral, whereas sodium ethanoate is mildly basic. Going to keep clicking on because there's a fair bit still to cover. Just a quick one on half equivalence then. So the only relevance for this on your exam would be adding a strong base to a weak acid. I suppose they could add a weak acid to a strong base just to be awkward, but it would give the same ultimate effect. Half equivalence is what we're talking about here. Basically, the takeaway point is that the pH at half equivalence equals the pKa of the weak acid. How does that work? Well, we have to go into the buffer calculation theory to look at that. Basically, when it's 50% neutralized, so half equivalence is literally when you've added as many moles of OH minus as there were half as many moles. So you've added half as many moles of hydroxide as there were moles of HA. So you're literally 50% of the way there. You're like halfway to having finished neutralizing the weak acid. And so at that point, at the midpoint, as it's labeled here, is at half equivalence, the volume at which you've added half the amount that you're ultimately going to need to neutralize the acid, you've got as many moles of weak acid as conjugate base. So this statement here at half equivalence, the conc of HA equals the conc of A minus, because you've literally taken half the acid and turned it into A minus, and then you've got another half still to go before you hit the equivalence point. And because of the way that pH works, like the pH of any buffer solution equal conc of H plus is Ka times the acid over salt ratio. Well, the acid to salt ratio is 1:1. So the H plus conc equals Ka, log that, or sorry, negative base 10, log that, pH equals pK. So how do you get that from a graph? You find the actual volume, so that's the value on the x-axis where the equivalence point is centered. Go to the middle of that inflection, divide by 2. What's the pH at half equivalence volume? That's the pKa. If you wanted to get into a Ka, you'd 10 to the minus pKa to make it Ka, and you're on your way. Again, check your notes. That's been a reminder. The only other thing there is to say on the pH front, really, from a practical perspective, is how to use a pH meter. So pH meters often need calibrating. So basically, you take 3 or 4 samples of known pH. You might actually go and make them. You might make some buffer solutions by doing a buffer calculation, weighing out the right amount, and saying, right, this is exactly pH, 4.5 or whatever. And then you'd see what your pH meter actually tells you it is. So you take your known pHs, you find out what the meter is telling you that is. You know the truth. The meter is telling you what it thinks it is. You can offset the error of the measurement because you know. So you can see the axes there, true pH, that's because you've made it yourself and you know what that is, versus what the meter is telling you. And so then you can take all your meter readings and convert them back into a more accurate pH just using a calibration like that. Moving on. Right, organic solid. This could be very waffly, and so I'm afraid there's no pictures here. I've just cut straight to it. You've got a lot in your notes about this. So if we're making an organic solid, i.e. something which has a melting point above room temperature, then it's almost certainly not going to be pure, because even if the reaction had completely finished, there's still bound to be some solvent, some catalyst, probably some unreacted reactants, maybe a side product. There's going to be like other stuff, contaminating up your product. So the first thing we do is dissolve our impure product, which is a solid, in hot water. And we try and use as little hot water as possible. Now, the purpose of that is to make a saturated solution of our product. And it also takes any soluble impurities in with it. Step 2 in this method, that again I've taken from an AQA question, once we've dissolved our product, if we filter that while it's hot, then any insoluble impurities will get filtered out, and so we've removed those. And then step 3, we're then going to take our solution of products, which has still got any soluble impurities in with it, we're going to let it cool down. And you could actively cool it with ice, or you could just leave it to cool down overnight. Either way, though, the point is that as it cools down, the solubility of your product in that solution drops. Because you used as little as possible solvent, and the solvent was hot, which made the solubility higher, when it cools, all that product can't stay dissolved. And so it crashes out of the solution as crystals, which you can then collect by filtration. And the idea is that if there are any soluble impurities still in the mix, they won't be there in great abundance, and they won't be saturated in the solution. So even though the solubility drops for them too, they don't crystallize because they're not saturated. So the idea is there's a lot more of your product than the impurities. Okay. Here's just some mark scheme. Oh, sorry, before I forget. Step 4 there, we collect under what's called reduced pressure. That is the kind of thing you might have to draw. Now, if you have to draw that for marks, you definitely don't need to be drawing the clamp stand, nor do you need to be drawing the rubber hose or the vacuum pump itself. We just draw everything like the flask and the funnel. What's good about this diagram is that it is sealed. Where the flask and the funnel meet, there's a bung, which closes the system. You do not need to draw the clamp stand. You don't need to draw the pipe or the pump, but definitely the hose as it is. Sorry, the Buchner funnel with a sidearm and the Buchner flask, and funnel, a sealed sort of system below the neck of the funnel. They're flat, so it's not one of those like cone-shaped filter funnels that are really common. It's like a flat bed, so the filter paper just sits flat, doesn't it? And there it is. That's quite a good image if you just ignore the vacuum pump and the hose and the clamp stand. Now, this was part of an exam question, and it was like explain the point of each step. So I'm not going to give you the actual question with all sub-marking, like the little sections, but things like, why do we use the minimum amount of hot water? Well, because we want the solution to be saturated with our product so that when it cools down, some of it has to crystallize out to enable crystallization, basically anything like that. Why filter it when it's hot? Because we want to remove the insoluble impurities, things like sand and grit and who knows what else. Or why filter it when it's hot? Well, because we don't want our product to crystallize too soon by cooling down. So why filter it, or why filter it hot? Cooling it just speeds up the process of cooling down. But more importantly, because you're cooling it below room temperature, you'll get a bigger drop in solubility, so you'll get more yield recovered from that solution. Why rinse it once you've been washing it on your Buchner funnel? Because there'll still be soluble impurities just kind of sitting on your crystals. And if you just give that a rinse with some cold water, that'll wash through. And then what you'll be left with are crystals that have just got water on them, and that water will evaporate or be pulled off by the Buchner pump. I'm going to move on again. Probably the longest one now, organic liquid. It all starts usually with a story of doing a reflux to make a liquid. And then the point is that liquid has got your product plus a load of other stuff in, a catalyst, probably an acid catalyst, and some other reactants and products. So the story starts with a reflux and making a mixture that has your product in. The next thing to do is to collect your liquid from the mixture using a separating funnel. But a critical part of this, and this is something to check your notes again, is that we use what's called a sodium carbonate wash. Now, I'm only going to say this in words, it doesn't appear on the slide. The purpose of the sodium carbonate is to neutralize any acidic components. So the classic here would be to make an ester, or maybe do something that involves an acid catalyst, maybe an alcohol and an alkene or something. And the sodium carbonate neutralizes anything acidic and turns it into something ionic. So can you imagine some leftover ethanoic acid in a reaction mixture gets turned into sodium ethanoate, which is ionic. It's got COO minus group in it. It's really soluble in water. So the sodium carbonate puts a load of H2O in because it's aqueous, but it also neutralizes all the acidic stuff. So the effect is that we tend to get a thin layer of low density organic, that's usually your product, floating on the top of a much bigger aqueous layer that's got anything ionic, anything that can hydrogen bond, pretty much anything except your products in it. So then we open the tap and we let the bottom layer out, which is usually the more dense aqueous layer, and leaving a little thin layer of organic on top, which is your liquid, but it's not quite pure yet. So then we might distill just the organic layer. So we discard the aqueous layer and we just take the organic layer and say, right, look, this is mostly our product, but who knows what else is in it. Again, they shouldn't be using a Bunsen burner there. This bit of clip art has got a flame that should be an electric heater. And hopefully you collect your product by distillation. And there's probably a little bit of water that gets carried over all that way, even though you've distilled it, which is why we then use what's called a drying agent. Now, a drying agent is simply an anhydrous ionic solid. And the classic is to use something like calcium sulfate, which is really insoluble, like it doesn't dissolve in water. It doesn't dissolve in organics either, so it's insoluble. But the anhydrous one will happily sponge up any waters to make little waters of crystallization. So you might imagine you've got CaSO4 anhydrous, and if there are any water molecules left in your distilled organic products, it will scrub them out, basically. It will be turning to calcium sulfate with 2 H2Os or however many waters of crystallization. But so the key steps there are you've made it, probably by reflux. You then use a separating funnel to collect it, involving a sodium carbonate wash to solubilize most of the rest of the mixture into the aqueous layer, where we get rid of it, distill it, then apply a drying agent, and then at the end of it, you can imagine you've got a pretty pure organic substance, a liquid, with a solid sitting in it. The solid's insoluble. So filter out the solid or decant it, just tip it without carrying the solid over, and you're away. Okay, almost finished. Not going to say much on this at all. There's one of the assessment practicals was about the test tube reactions for the transition metals. We've got some good notes on that. Go and learn the colours, be aware of the equations, and all the connected theory as well. I won't say any more on that. And then TLC, which is quite a nice way to finish it. The only things I'd really want to remind you of here, because the theory was reasonably straightforward, was that how TLC actually works. So it's all about this balance that molecules have between their affinity for the mobile phase and for the stationary phase. And a molecule's polarity ultimately dictates how soluble it is in this or how attracted to that stationary phase it might be. And so we tend to use a contrast in chromatography. If you've got a polar mobile phase, then you're going to have a non-polar stationary phase and vice versa. And it's usually a polar stationary phase, to be honest. But it's all about the molecules' polarities. And the favourite here is to mention amino acids, like, and use them as the example of the molecules that get separated. In TLC, it's almost always the case that the solvent we're using is some kind of flammable organic substance. It might also be toxic. Therefore, we'd use a fume cupboard and we'd keep it away from naked flames. Obviously, there's no need for heat in a TLC experiment. We're not boiling anything, but keep the Bunsen burners away. But a fume cupboard, that's a good shout here for any smelly, possibly toxic solvents, organic solvents. And you can check your notes on RF values. The other thing I'd remind you of here is, even though it's not an assessment practical, we've also had a quick mention of column chromatography and gas chromatography, which are on the spec. They just weren't assessed practicals. So that is pretty much it for your whistle. Oh, sorry, and on TLC as well. How do we find the spots? Well, we use a UV torch. There are some other options. There's a chemical called ninhydrin that can be used. You'll see it on mark schemes, but UV light to locate the spots, circle them with a pencil, and off you go. And then you know about RF values as well. When we do TLC, you could either look up your RF values in a data book, if such a thing exists, or you can just put exact known samples of the pure substances on. So in this idealized example here, you can see the 3 points on the left are all labeled as known standards or reference compounds, and it looks like this mixture contains all 3 of them because the spots match, but you could calculate the RF and compare them. That is it. I hope you found that useful, or at least in part. I really didn't think you need to be reminded how to do a titration, but it doesn't hurt to just have a look at everything that could turn up. You know what's already turned up on papers 1 and 2, and that might just serve as a bit of a flag for these last few days of revision now. Hope at least part of this has been helpful. All the best, guys.